Hop, hop. C'est bon. Ok. L'allumer et le couper.
Oui.
Est-ce que j'en prépare un autre pour les questions, peut-être?
Ouais.
Ou tu passeras le tien.
J'espère que tu auras qu'il y a...
Normalement, oui. On est directement dessus.
Did I use the right one?
Okay, so hello everybody. Thank you very much to be there for this exceptional seminar of Ken Kamrin, who is working on granular flow, as you will see right now. And he was first at MIT, and now for 1 year, 2 years, he's now in Berkeley. Okay, and so please, Ken, tell us about continuum modeling of dry and granular material.
Wonderful. All right. Well, thank you, Pierre-Yves. Hi, everybody. So first of all, thank you for getting the screen working. That was very impressive work. Very, very good cooperation. I like that. So I'm Ken, and I'm going to tell you about meshless continuum modeling of dry and wet granular media. And so here's how I think I'm going to explain this today. So I'm going to start out with dry material, and I'm going to try to warm you up to the methods that we use for the dry case so that it's a little more clear what happens when you add the fluid. So start dry, then add fluid. That's my plan. And when I add the fluid, I'm going to have to review, perhaps teach two-phase mixture theory if it's new to you, and then give you a sense as to what it looks like with both liquid sediment mixtures and gas sediment mixtures. Okay? So I don't want to assume anything about what you come in knowing. So I'm going to start by teaching you a little bit of granular rheology, just a little bit, enough for you to get the basic ingredients so that you can see how you can put them together into a solve. All right? So everybody, imagine you've got granular media. Just think of dry sand or marbles or something. And you squeeze it between two rough plates. You assign the pressure P. Okay, so you assign P. All right, you assign the shear stress tau, and then at steady state, you'll get some shear rate gamma dot. And so you might ask, what's the most generic constitutive relationship that would relate all these quantities, right? And so, there's a lot of development on this topic, and there's a lot of different details that go into it, but they all kind of have one thing in common. And so I'm just going to make a model out of the most common ingredients of granular materials, and I'm going to show you what that would look like. So first of all, there's some kind of a frictional flow rule. All right, and what that says is that if you're flowing at all, then this ratio is some material constant. Now, of course, more developed models will say it's not quite a constant. It could depend on rate. There could be size effects. There could be history effects. But for simplicity, let's just say there's a single internal friction called mu s. And if tau is less than mu s times p, I say no flow. Okay, so that becomes my frictional yield criterion. So if I'm squeezing hard enough, I have to shear hard enough to get it to flow. Now, another important part that's often not mentioned in soil mechanics textbooks is this very important thing, which is that you cannot pull on sand. Okay, there's a no tension criterion, so you cannot pull on it. So how do you quantify that? Well, let's say that there is some close packed density called rho c, which is characteristic of the material. And if rho is less than rho c, I say no stress. All the stress must be zero. Now, of course, that's also a simplification, right? So in a typical gas, the particles are not in contact, but there's still a pressure because there's all sorts of fluctuational characteristics that can give rise to stress, even if you're not in contact. Most granular materials are not in that limit. And when the material is separated, it really is close to zero stress. All right, so believe it or not, these two simple rules are, in my view, the simplest ingredients of any granular flow model. And it's enough to actually make a model. So what would a model like this look like? How would you put it together? So I'm going to introduce to you a little bit of the framework for how you would do this. So my background is a mixture of solid plasticity theory and fluid mechanics. And so one of these is going to make you uncomfortable depending on your background, okay? Sorry. But this type of model I solved with elastoplasticity. So in that view, I take this information as the flow rule, okay? And that instructs this very complex dashpot in my picture. It's in series with the elastic part. There's always an elastic part in the background, such that when I'm beneath a yield criterion and the dashpot is closed, I still have a well-defined stress because I always have the spring in series. So this is like a very complicated version of a Maxwell model if you're familiar with viscoplasticity. Okay, so number one, I treat all of this with an elastoplastic decomposition. Now, you will not usually see too much of the spring because it's so stiff. Okay, it looks rigid when I'm not flowing, even though there is a small strain there. Okay, make sense? Good. Okay, so this plastic part of the flow looks like almost all of the flow. But so I might just call it the flow, even though technically it's only the plastic part I'm referring to. We assume codirectionality, which is also an approximation. I'm just trying to show you what the simplest dry model would look like. So that is to say that the plastic flow rate tensor should be aligned with the stress deviator. If I push this way, it should deform this way. That's an isotropy characteristic. Are real granular materials isotropic? Again, not exactly, but close, okay? There are structural state tensors you can invent to help you get the alignment between the two fields more precise, but this is a simplification. And then lastly, in this picture, I mentioned pressure, shear stress, and shear rate. But in the 3D tensorial form, I need to make general invariant quantities for those. And so when you think of tau, you should actually now think of the equivalent shear stress of the stress state. P is the hydrostatic pressure, and gamma dot is the equivalent shear rate. So now that lets me take this picture and put it in a form that I can now simulate. This is a completely closed model now. All right. So how do you simulate a model of this type? So you have to think it's going to be difficult because what I'm really doing is solid plasticity up to the levels of absolutely enormous strains, hundreds of thousands of % strain, right? So normally when you do solid plasticity, you would do maybe finite element or something, and there a large strain might be a few 100%. But this stuff is going to flow more like a liquid. So I need machinery that's okay with those huge deformations. And for that reason, in my group, we've become very accustomed to what are called meshless methods or mesh-free methods. And there's a couple that we use. We use something called MPM, material point method, and something called SPH. But MPM is the one that we've done the most with, and I'm going to focus on that. Raise your hand if you've ever played with the material point method. Do you know MPM a little bit? Yeah. So this is going to be my 2-minute educational pedagogical slide on how MPM works. Sound good? So here's how MPM works. Here, I'm going to talk you through what one update of MPM looks like. So in MPM, you don't have a persistent background grid. You don't have a persistent mesh for the object. What you have are a persistent set of floating points. Okay? We call these the material points because they're supposed to represent actual material points of the continuum. Think of them like tracers. All right? So here's what happens during one step. So the tracers store all the real continuum data, velocity, density, stress. They all live on these points. So the first thing that you do, and this all happens within one step, is you impose a background grid. So we call that the scratch pad. Then what you do is you use interpolation functions to take the data from the points and put it onto the grid. So now the grid has all that data on it. Okay. Since the grid has the stress, the density, the velocity, right now I have everything that I need to do one finite element step. Okay? So I balance momentum, I apply the constitutive relationship from the prior slide to literally update this grid. But I only do it for one step. All right? I then take the data from the updated grid and pass it back to the points using the backward version of those interpolation functions from before. So now the points have all moved. The points are all updated, right? And at that point, I kill this grid, and I'll start fresh, next step, with a clean one. Do you see how that works? So one step, you'll never see this grid. You'll only see the moving points, but it was introduced and destroyed every step. Does that make sense? That's how to think about MPM. It's like a floating finite element step. But because the grid is not persistent, I don't get persistent mesh deformation that would cause all the errors that I talked about. Everything is persistently maintained only on the points. So here's what it looks like if I take the very simple granular continuum model from the last slide and implement it with MPM. Okay, so this is complete emptying of a silo. This is shooting a bullet into a bed of grains. And remember that this stuff right here is in that open state, right? The stuff that's falling is stress-free because its density is below rho c. Now, your eye is going to probably try to tell you that you're seeing individual grains of sand falling, but you have to knock that out of your head. Those are continuum tracers. This is a PDE solver, right? And so this right here, it's splashing and reconsolidating and doing stuff that might look complicated to your eye, but the code doesn't think so. All the code knows is there's this rule, and there's these points. Okay, and the points have a constitutive relationship that transits easily between a dense plastic flowing state and an open stress-free state. And when the density gets high enough again, it switches right back. So for example, you can do 3D version of this. This is something called the J-hooking phenomenon. So if you take a solid ball and you shoot it at an angle at a bed of grains, sometimes it will ricochet back out. And this might remind you of stone skipping if you go to the lake and you take a stone and you skip it over the surface. But the difference here is that it actually goes into the granular media. A drag-induced lift forms and then it pushes it back out. So it actually goes into the material. It doesn't stay on the surface like a rock on water. And this is an example of a wheel driving over the continuum of granular media. My student Aaron forgot to remove the wall. But I actually like it. Look at it. It hits the wall and does exactly what you would expect. So what can you do with this? So I'll just say, and I'm not going to talk too much more about the dry model. I mostly am showing it to you to get you warmed up, all right? There are a variety of places where that very simple dry model with just a friction coefficient and a critical density actually works very well on its own. Typically, it involves intruder dynamics near a free surface. So if you're interested in how an object interacts with granular media, and you're mostly interested in the object's motion as opposed to getting a precise flow field in the grains, I'm willing to say that this model usually works pretty darn good if you do have a cohesionless granular material like sand. There's a variety of other things you can do with this, like scaling laws, because it's so simple. The resistive force theory, it's able to explain simple empirical rules people have been using. But one other thing you can do with a model like this, because it works for intruder dynamics, is you can develop a 3D code and use it as a way to sort of engineer things in environments you can't recreate on Earth. So for example, we've had some work with NASA to produce a code where they can simulate rovers and infrastructure devices on the moon. So this is the Viper rover, which was supposed to go to the moon, but who knows anymore thanks to our friend Trump. And this is lunar regolith simulant. Okay, and what does that mean? It means we have data from when the Apollo astronauts were up there for what's the friction coefficient of the material. We have data for what its critical density is. And then, because it's all on my computer, I can actually use lunar gravity. And I can actually simulate the whole thing. Right? And this might be useful if we ever want to put a colony up there and you want to know what it's going to be like to build on the moon, right? So, for example, this is, don't ask me why, but it's a Viper with plow capabilities. And you can see the difference between a flat versus an angled plow. This one is actually stuck. Do you see the wheels are spinning out? And this one is fine with the angled plow, right? So the hope is that the simulation is going to basically take the role that normally experiments would do on Earth, because it's very difficult to change the gravity on Earth. And essentially every technique we've tried has crucial flaws. There's a flaw with most techniques. You know, sometimes you can do drop tower tests, but you only get a few seconds. Sometimes you can do centrifuge tests, but those increase the gravity, generally speaking. You know, sometimes you can do air, but then that makes the particles wiggle in a way that's very unnatural. You can do the parabolic flights, but it's impossible to keep it on a perfect parabola. It's always wiggling back and forth, and you start getting violations of basic granular physics in some of those tests. But what's nice about the computer is as long as you believe the continuum model, and that's the big step, you can just change the gravity with a couple keystrokes. So far, so good. Any questions before we start adding some water? Yeah.
What are the limits of the approach, of the NPM approach?
Oh, just the numerical approach?
Not numerical, physically. What are the limits?
Oh.
Okay, you discretize, you come back to the tracers. I guess there are always limits.
Yeah. So one thing, have you ever seen the movie Frozen?
Yes.
You know, that was all the snow was NPM.
Okay.
Okay. So one thing that happens, not so much with a cohesionless material, but more with a cohesive material, is if you pull too hard, there will be an element that's empty just by the fact that the points inside have separated outside of the element. So let's suppose it's a different model. It's like a rubber model or some solid, and I'm stretching it. It's possible that I'm going to have an empty element, right? And all the points are now outside that element, even though it was supposed to be one solid object. Well, NPM is going to see that as being open space, and you'll get artificial fracture, okay? So with NPM, there are strain limits, okay, for the solid phase, where if you strain too much, you get artificial fracture. So if you look at like all the snow in Frozen, you know, they throw it at people and the bits all fall apart. That's all numerical artifacts that were tuned by artists to look like snow. And they were using the point density and grid density as a tuning parameter to make different kinds of snow. Okay, but that's different. That's cohesive material. It's supposed to be able to stretch and stay one body, and they used it as a way to break it apart. But this material breaks apart on its own because once the density drops, it's stress-free. So one of the benefits of doing NPM with granular material is that its cohesion-less response is stress-free. So it automatically gets it right, even if it makes a gap, because there's no stress. But the answer is there's supposed to be no stress. Yeah. So, but in the general application of NPM, there's a strain limit to making it stay together as one solid. Yeah. The other question that you hear a lot is, how do you know how well it's converging? So there's a lot of moving parts, right? There's the points, there's the grid, and then it goes back to the points. So one of the challenging things with NPM is getting a clean, analytical, on paper, convergence criterion. Because the points are moving, so where they're located in the body is changing, and where they're located within each box is changing. It's not like finite element, where you have very clean Gauss points, and you can do the analysis very directly. So I would say the convergence criteria, I mean, you can show it's converging, but proving on paper that your exact case is converging is something people are working on. Yeah.
And what about boundary conditions?
Well, one of the great things about this is the boundary conditions are handled by the grid. So whatever you would do in finite element, you would do here. And if you don't do anything, you get the traction-free one. So when you hit the surface and it splashes, you get for free the natural BC. Yeah. Yeah. Sorry. Yeah.
What is the continuous model? What about the continuous model? Because you have your points, right?
Yes.
And then you pass it to the grid.
Yes.
And you are solving the thing on the grid, right?
That's right.
And what is
Sorry. What was I using for that? Yeah. So I was using that frictional plastic rule, right? So if you're dense, you obey plasticity. If you open, you're stress-free. That rule in 3D that I showed you was implemented into the code, and you combine that with momentum balance, divergence of sigma plus rho times g equals rho times v dot. So it's a perfectly dynamic coupled solve, right? So it's just like I would do a finite element solve, for example, where you balance momentum and you apply the constitutive relation. And that happens in the finite element step. That's one of the good news about NPM is the points. Some people split points and merge points. I don't, because you might lose mass. But these points always hold their same amount of mass. Okay, so the mass is always conserved because each point always has the same mass. The volume it represents, its density can change, but the mass can't. So as long as you don't annihilate points or merge points, there's no worry about mass conservation. It must conserve. Just like how in, for example, finite element, you don't worry about mass conservation because all those nodes are still there, right? Only when you start killing off elements would you worry about that. So the good news is with these mesh-free methods involving points, you will automatically conserve mass as long as you don't try to get too clever and merge points or divide points.
depends on the problem, but you need a large amount of points.
Yeah, you need at least so many points per element to stay accurate. Usually in 2D, you would say about 4 per element's fine. 3D, about 8. Yeah. And the good news is for us is if you separate beyond there, the correct answer is no stress, but that's the one you'll get for free anyway. So it's a very lucky coincidence, actually. Yeah.
In your presentation, you said you have a very stiff elastic.
That's right.
Does that affect the stability of the tiny compression?
It absolutely does. Yeah, you get CFL constraint just like you would normally. Yeah, so that's what limits me, is how stiff the elastic response is. If I want to cheat, which sometimes I will do, if I don't care about the acoustics, sometimes I do care about acoustics. We did a study where you could see the wave coming out when you hit. You can want to make sure it passes through correctly if you want to do the acoustics. There you can't cheat. You have to use the real elastic response. But if I'm mostly just interested in flow, and I really need the elasticity there to get a well-defined solid-like response beneath the yield criterion, that's where we start to cheat. I make the Young's modulus lower so that the time step gets longer, just like I would for finite element. Great. All right, so maybe we'll continue. That was good. I like that. That was nice. All right, so let's make life really difficult for ourselves. Let's take a hard problem and just make it even harder. All right, so let's suppose I have grains in a fluid. Now, how would I simulate this? So your first reaction might be to try the direct solution, okay? And the direct solution would be something like an LBM DEM solver. So here, these are actual grains. This is actually what I call, I don't know if you have this term in French, the whole kitchen sink, where you're literally doing absolutely everything. I'm modeling every single grain. I'm modeling all the fluid around every grain and the interaction between the fluid and the surfaces of every grain, okay? And there are ways to do this. One example is LBM DEM, where LBM is solving the fluid phase, DEM is solving the solid phase. And this is an example of a problem we did with Schlumberger, pushing slurry through a valve, right? And it's very interesting and it's very precise because you're doing everything. But the problem is it's extremely slow. This only had 50,000 grains and it took us 3 weeks, what you're seeing right now. Okay? And that's because you're asking so much, right? You're solving like Navier-Stokes between every pair of grains, you know, the whole field. But it is quite accurate. And it's nice because it can extend experimental data sets. So this is something that we did recently. So this is an experiment with riverbed gravel, and there's water flowing over it. And we wanted to study the transport, the erosion of the riverbed. And we had an undergrad take 1,000, go to the river and actually gather 1,000 particles of riverbed gravel, CT scan them, and then we mimicked them by overlapping spheres to create avatars of the actual riverbed gravel. And that's this simulation up here. And we were able to show that we get like a very nice agreement between in our experimental flume with riverbed gravel and our simulation. Okay, so again, you can do this. It does a very good job replicating experiments, but I'm too greedy for this. I don't want to have to wait months to get the answer. I want to wait maybe 30 minutes or an hour. Okay, so that pushes me into the world of continuum modeling. So let's suppose I have granular media and it's submerged in a fluid, and I want to model this as a continuum. And you might say, what are the options available to me? So the first set of options you might consider are what I call the single fluid or single solid models. So how do those work? So in a single fluid model, the fluid and grains are believed to move with the same velocity, and they move as one effective fluid. So have you ever learned suspension theory? I call that a single fluid model. I imagine that the average motion of the fluid and the average motion of the grains is the same. So I'm treating it as one effective material with its own effective constitutive relations. And there's been a bunch of work on this in the sort of dilute and more recently the dense limits. Okay, but that's one option. All right. Another option is what we call the single solid models or the poroplastic models. So those are models where I say what controls everything is the motion of the grains. So that I just follow the grains as one solid object. And I just think of the fluid as like this state that fluxes through. Okay, so it's really, I could do the whole thing on finite element. I treat the solid as what's moving, it's the master. And the fluid is just this extra variable that sort of squirts through the solid. has a pore pressure variable and it obeys some kind of Darcy law, but I don't solve momentum balance on the fluid. I treat it as just some extra field that has fluxes through the solid. And this is essentially what is the foundation of what we call poroplastic modeling, right? But again, the issue with these two approaches is independence of the two phases, right? So think about a problem that I might want to solve. Like, you know, let's suppose I want to do this, all right? Like a real life problem. So there's going to be some material which is mixed, where it's true mixture of fluid and solid. Some material is just pure fluid. And some material out here is just pure solid. And they can move relative to each other. So to me, if I want a better solution to, say, the brute force or kitchen sinks problem, I want a continuum model that lets me capture both phases. So we call these two-phase models or mixture models. And there, the behavior of the grains and the pore fluid are independent. And they're just coupled together with interphase forces. So I'm going to have a continuum model for the solid phase. That's my granular media. And like another continuum model for the fluid. And they're just going to talk to each other through coupling forces. And there's been a lot of work on this. Let me just give you a little teaser movie. Or actually, before I do that, let me tell you what the complication is in doing this. So number one is you have a lot of constitutive models you have to write. All right. So for example, I'm going to have a constitutive model for what the solid phase is in the presence of a fluid, and the fluid phase in the presence of a solid. And also, what's the drag relation? How do I couple the two? How does the motion of the fluid against the motion of the solid cause a force? These are things I'm going to have to figure out to do this. And it will require some new simulation techniques. I have to somehow run a model which will do a continuum fluid and a continuum solid at the same time and couple them correctly. And so, keeping in mind, numerically speaking, there's going to be probably a difference between what I would use to solve a problem like this, a liquid sediment problem, and a problem like this, a gas sediment problem. For example, the liquid, you know, it has an important Lagrangian feature, like it has a free surface that can wave around. Whereas gas is usually space filling, but it can be at higher Reynolds number, right? Get more mixing. Perhaps it's even thermally sensitive. Okay. All right, so let me just give you a little teaser for what you're about to see next. Okay, so this is just an example of what we have in mind. So it's a nice warm day. Okay, you go to the beach, and here's the beach, and you're standing on the dry sand. There's the dry sand. Okay, and you look ahead of you and you see the water. And you don't see it, but underneath that layer of water is what we call mixture, wet sand, fully saturated sand. And in fact, that mixture goes all the way back and forms what we call a water table that you don't see, but is under your feet. Okay? So you're going to see a movie, I'm going to play it in a moment, where you drop this block. We're just going to watch what happens when this takes place. Remember, you're seeing two sets of material points now. The ones that are colored are the material points of the granular solid phase, and these little dots on top, that's the fluid. Okay, so here's what happens. So now you're going to get a sense as to what we're talking about. Okay, so you drop the block, you get shearing and slope instability that pushes against the water. Now the water is stirring. But it also depresses the water table, so now there's a head gradient, and so the water is going to push through, okay, to try to equalize the head. Okay, just wait. It's going to flatten out that water table again because of the pressure. So you have granular plasticity and fluid totally interacting with a pore drag law that equalizes in the end. That's what I'm getting at, okay? So two continuum models at the same time talking to each other, hopefully correctly. All right, how do you do this? Okay, so here is an element of material that is what we call a representative element containing the grains and the fluid. Now, by the way, how much time do I have? Got it. So if I start going long, just pull me off. Okay, so this is the continuum element that we're going to focus on, a saturated granular element. So here's how to start. First, I imagine that element is decomposed into its solid part and its fluid part. So the solid part looks like this, the fluid part looks like that. And then I'm going to re-homogenize each of those parts into their own continua. Okay, so I'll have a continuum representation of this solid, the continuum representation of this fluid. So the continuum representation of the fluid is not the continuum representation of this material here, it's this sort of porous fluid body. So it's going to depend on the value of the porosity, right? Just like this is like my homogenized continuum. So let's have a look. So the way that this works, I'm just going to teach you continuum mixture theory for a moment. I have a solid phase, I have a fluid phase in my simulation. Wherever they overlap, it's mixture. Wherever the fluid is on its own, it's going to be pure fluid. Wherever the solid's on its own, it's going to be pure dry granular media. Some people ask, do you have the partially wetted phase in this? And the answer is, I'll just tell you, no, not yet. Okay, I don't have sandcastles yet. I have saturated granular media of any porosity, but saturated. I have pure fluid, pure solid. And so we have a porosity measure called N, which at 1 it's full solid, at 0 it's pure fluid. So you can then define things from what I showed you on the previous slide. So you can define a homogenized solid density, a homogenized fluid density. And you can decompose the total stress in the element into the part that comes from solid and the part that comes from fluid. And what's interesting is the solid part can be further decomposed. So here's my solid part. We say that there's 2 contributions to a wet solid stress. One is called the effective stress, named after Terzaghi. Okay, and that is the stress born from the contact forces between the grains. Now this is called the pore fluid correction, right? And that's because if you look at the stress of an individual grain, there's stress coming from the contacts, but also the fluid that is under pressure and squeezing on it too, okay? And that's what this is. Now, when I do constitutive modeling, for example, I want to get rid of this part because what determines if I flow is actually this part, right? This part's just squeezing everything. I need to just sort of get rid of that in the solid stress so I can focus on that. And similarly for the fluid, you can decompose the fluid into a shear part and a pressure part. Mass conservation. So to conserve mass, you have to calculate mass balance following the velocity of each phase now. So this is mass balance where that derivative with an S means you follow the flow of the solid, and this one with the F follows the flow of the fluid. Right. But again, mass balance is pretty much free if you use MPM. And importantly, we have now momentum balance. So the solid body and the fluid body must each satisfy their own momentum balance equations. All right, and so each on its own looks sort of familiar. You have in the fluid phase, you have divergence of fluid shear stress. You have a buoyancy correction. You've got gravity. And importantly, you have drag forces now from the solid on the fluid and vice versa, such that if I were to add these 2 equations together, the drag forces and buoyancy effects would cancel, and I'd have a perfectly fine right-hand side for a momentum balance. So the coupling forces between the phases satisfy Newton's 3rd law. This is the opposite of this, and the coupling of this to this cancels, so that you would have buoyancy self-canceling and drag forces self-canceling. So what do we have to do, right? So this all comes from mixture theory. I did not invent any of this. But what we do have to get is constitutive relations. So I need to get a relationship for sigma tilde. Okay, how does that relate to the flow? Remembering that the effective stress is what should be relating to the flow. I need relations for the fluid stresses, both its shear and pressure part. And I need a formula for the interface drag force. That's like Darcy's law, right? Of the force of one dragging on the other because they have different velocities. All right, so let's go ahead and just summarize how we're going to do that. So the drag interaction. So in the drag interaction, what I need is a force of one phase on the other if they're not moving with the same velocity. So for that, we're going to use something called Beetstra's model, right? Which is a very advanced version of what you might think of as Darcy's law or the Kármán-Kozényi model, where it's proportional to the difference in velocity between solid and fluid phases. So if you're looking at one location and the fluid and the solid have different velocities, their difference is what gives rise to that drag. but it's scaled by something that's packing fraction dependent and Reynolds number dependent. But those are all things I'm going to have access to. So I can actually apply that model in full as my drag law. Good. Okay. And now I need a model for the fluid stress. So I need to take what's happening here and calculate the average stress in here. And for that, I can actually use something pretty simple. I can just use the effective viscosity formula from Einstein. So Einstein at least came up with the first order correction to this and said if you have a fluid, but there's particles in it, and you say what's the average stress in just the fluid part, it has this correction, it has this packing fraction correction. So we're just going to adopt that. And for the fluid pressure, we have a couple options we can use. We can do something simple like a barotropic model. So we can look at how much this is not incompressible. So the fluid can compress and the compression can give rise to the pressure. Or I can use, if it's a gas instead of a liquid, I can use like the ideal gas law. And this is the ideal gas law written in terms of internal energy and the constant gamma. So you have choices, and I'll use them both depending on what the material is going to be. Now, the fun one. How do I model the stress in the solid phase? So that's why I did the dry part first, okay? So that now you can see what I'm going to modify to model the Terzaghi effective stress. That's the stress gotten from contact forces and how it relates to the flow of the solid. Sound good? So again, it's one of these tweaked Maxwell models, okay? It's elastic with a plastic part. And the plastic part is sort of similar except for a couple important differences. It's similar because I still allow free expansion and compaction just like I had before. There's a critical density. If I drop below that density, I can expand freely with no stress. I can recompact, and when I get to the right density level, somehow the plasticity law turns back on. But importantly, when I do shear, I'm going to make one change. All right, one change to the dense flow rule that's very important. Well, actually two changes. One that's really important, which is I'm now going to allow the model to have shear dilatancy, which is something that I didn't consider before. Before I said when I flow incompressibly, right, if I'm in that dense phase. But now I'm going to say, look, in reality, if I'm at a certain high packing fraction, when I shear, I open. That's called Reynolds dilation. If I'm at a very fluffy packing fraction, when I shear, I will contract. Okay, and so the total volume state, which is in this isotropic part of dP, is a combination of, I can be densely dilating, or I can be expanding or contracting freely. And so the question is how are you going to model the shearing and the dense dilation? So let me show you. All right, so when I was doing dry, remember just a few slides ago, when we were dry, the dense phase looked like this, where I called that a constant. And that was the end of the story. There's nothing else to it. I'm going to do two things, okay? If the material can dilate, there's something called the dilation angle, and it modifies the strength of the material in the following way. So now the effective solid stress is gotten as a multiple of the effective pressure, but the multiple is not a constant in two ways. So the steady state response, I'm going to model that a little more precisely. And there's also going to be extra friction due to the shear dilation. So what does it look like when you put that all together? Right. So for this, I'm going to go extra precise if I can. I'm going to use something called the mu-I, mu-V relation. Because my material can be dry, my material can be saturated. And I'm going to include rate effects now that I never included in the dry model because I didn't care as much. Okay, but now I do care a little bit more. So there's now a relationship between the steady friction coefficient and these things called the inertial numbers, which are basically rate-dependent dimensionless numbers. One that is dependent on the viscosity and one that's not. And this is the one that's important when I'm dry. This is the one that's important when I'm wet. And in general, they are mixed. So that's the model I'm going to use there. And for the dilation, I'm going to use a very simple, something called a Rudnicki-Rice type model, where I say that the amount I dilate depends on how much my current packing fraction exceeds something called the equivalent, which is what I should be at steady state. So if my current packing fraction is really tight, then as I shear, I should open, right? And that's going to make this number positive, and now beta's positive. If I'm very fluffy, as I shear, I contract. That makes beta negative. And the equivalent packing fraction is some special property that at slow flow is some special value for the material. And as you flow faster, it gets lower. All right, so I know that's a little complicated, but let me just show you what happens in a model of this type before I introduce the fluid phase. So let's suppose all I did was, let's suppose I make this mu relationship constant again, like I did for the dry. So don't worry about all this complication. Let's call that a constant. But I'm going to include this beta term in the model so you can see what it does to the solutions. And let's just look at the dry case. So here's an experiment of a plow in undercompacted material. So this is very fluffy material. And here's the same experiment, but they compacted the material down so it is very tightly consolidated. And then here are the corresponding videos of my movie, where all I did was take the dry model from before and add the beta correction for the dilation effect. Okay, so let's take a look side by side of what happens. So there, see how smooth that is when you're under? And this one also gives me a nice smooth response when I'm under. When I'm over consolidated, look how jerky it is. And then this also gives me that jerky response. Watch it again. So smooth, that's under. Nice and smooth. And this is over consolidated, moves in little bands, as does the continuum solution. So why is that happening? Well, if I'm over consolidated, I shear weaken, right? Because the material opens as I flow. And if the material opens as I flow, the apparent friction is dropping as I flow. It looks like shear weakening. That's going to form shear bands. On the other hand, if it's very dilute, when I shear, I compact. That means I shear strengthen. That's a strengthening mechanism. That actually fights shear banding and gives me smooth solutions, whereas this one gives me bands. And you can really see it. Perhaps you've tried this yourself. If you ever tried to shovel really compacted granular media, it's like little bursts, right? And that's because you have to move it as a sequence of shear bands. Whereas really fluffy material, it's a nice constant force you apply to shovel it. And that's because of the dilation effect. Now that I've done this, I'm going to then, okay, so maybe you have some intuition now. Maybe you don't. I'm going to put all the pieces together and tell you what this mixture model can do. So first of all, one thing I can tell you for certain is, without having to do any numerical simulation, is that it's going to get certain limiting cases. Number one, in the pure slurry limit, if you just have a dense slurry that you shear between porous plates, you're going to get it exactly correct because I've engineered it this way. You're going to get the so-called mu-IV relationship because we designed the model that even in this limit, I don't even have to solve it numerically to know that I'm going to match the experiments of what people found when they plot mu versus this inertial viscous number called IV. And that's the pure slurry limit, I call that. It's also going to match the extended Einstein suspension rheology. So remember, we knew we were going to get Einstein. That's this limit down here for low packing fraction. That's if you just have a dilute suspension now. So this is what I'm doing now over here. I have a dilute suspension, and I'm looking at the effective viscosity versus the packing fraction. So when packing fraction is low, you get this, which is the Einstein rheology, this part down here. But because of the coupling to the solid phase, right, I know it's going to do, I can calculate this. I get this red line, which is going to start to pick up automatically and matches the data that we have as you look at the effective viscosity of suspensions as the packing fraction gets very high. So that much I know I'm going to get for free. But now everything else, I'm going to try to use simulation because I can't keep generating solutions in my head. All right. So here's how we do it. I've got the solid phase, I've got the fluid phase. They sit on top of each other. I think of them as two separate continuum bodies. Each I'm going to discretize with material points. All right. And then they're all together on one background grid. And the background grid is how I'm going to exchange the information that I need to get the right coupling forces between the two phases. So let's do some validation tests. So back in 2009, Palha and Puliken did a study with simple beads in water. And what they did was they had a layer of this stuff and they would tilt it and they would watch it avalanche. And they had a really good data on this. In fact, the data was so clear, we were able to calibrate the entire model from it. So it calibrated all the parameters in the model. Fantastic. Okay, But that's not the test. The test is, with the calibrated model, can you now predict a different experiment that also claims to use beads and water? A couple of years later, Rondon et al. Did this test. Here's what they had. They had an aquarium, and they had granular media behind a plate. Then they lift the plate, and they watch it splay out very carefully, right? And what I really liked about their experiment was they didn't just follow the motion of the pile. They also had a pressure sensor in the corner. So you could see the fluid pressure changing while the material is flowing. And of course, for us, we will know that as part of our solution. We're actually measuring the fluid pore pressure along with everything else. So we can really see if we get it right for the right reason. All right, let's have some fun. Okay, so over here, I have two simulations that are going to play. The only difference between these two simulations is the initial packing fraction that I assign to the material in the corner, okay? Here I assign a high packing fraction of 0.6 initially. Here I assign a low packing fraction of 0.55. People are always amused that 5% can be the difference between a large and small packing fraction of granular material. But it actually really is a huge difference, okay? So here's the deal. I'm gonna give you 5 seconds, okay? Try to guess what's gonna happen when I press play. All I've done is changed what I assign as the initial packing fraction. Otherwise, all the same constitutive relations. Okay, 5 seconds. All right, here goes. I won't make you tell me if this is what you thought would happen. A huge difference, right? This is why I went to the effort of putting dilation into this submerged model, because it makes a huge difference when there's fluid there. Watch it again. So you might ask, why is this one struggling to flow, but this one flies out no problem, right? Well, let's see if I can get a picture for this, right? So this guy starts over consolidated, right, above the equivalent packing fraction. So for it to flow, right, it's going to shear. It wants to shear. For it to shear, it must expand because it's over consolidated. So it's going to shear dilate. But then it's going to have to suck fluid in because there's all this conservation going between the two phases, right? So the fluid will suck in to fill that space. That puts the fluid in a state of suction. What that then does is it tightens the pressure between the particles. It makes it even harder to keep flowing. So the interaction with the fluid really makes this go slow and this one go fast, right? Because here the fluid squirts out as it flows because it shear contracts. That helps it continue flowing because it reduces the pressure in the contacts. So in one case, the fluid makes the contact stress go up. In the other case, the fluid makes the contact stress go down, okay? So now if we're right about this, we'll be able to see it in that pore fluid sensor, right? So here's a comparison of experiments to simulations from when they did this in the lab. So this is the 0.55 case versus the 0.6 case. We were really happy to see that it like totally nailed it, right? That's the front position versus time for the two different cases, all right? So, but like I said, it's not important that you nail it. You have to nail it for the right reason, okay? So here is that pressure that they measured in the back corner. So if this is what I think it is, in the dense case, the pore fluid pressure will go tensile, okay? It's gonna go negative, it's suction, right? And that's exactly what you see. It goes negative, okay? In the underconsolidated case, it squirts out, so the pressure in the fluid phase goes up, right? And then because of the combination effect of the Terzaghi and fluid part, that makes the contact stress go down, and that's why it flows so fast. But indeed, both do the right thing. And both were modeled correctly with the model. Yep.
Do you understand why the frequency between the simulation and experience increases with the simulation system side?
Sorry, say that one more time.
It seems, okay, sorry, it's a very rough observation.
Sure. Oh, you're looking at these two different.
The discrepancy increases while your resolution increases.
The discrepancy increases as the resolution increases. Yeah. Is that generically true? I think the solid, it might be truer on one side than the other. Yeah, I can't, to be honest, I don't remember why we did two grids here.
Yes, you're right.
Yeah, I don't know if it's systematic, yeah.
Okay.
We did a follow-up paper using a different method for the fluid phase, and it resolved most of this. I'm actually going to show you after this part how we fix some things with this. Yeah.
But you have the initial condition with the, the plate that they are moving.
That's right.
Which might play a role.
Yeah, exactly. All we did was just snap our fingers and make the plate disappear. We didn't actually simulate it moving up. But that would have been cool, actually, to do that. Yeah. Okay, let's get weird. Okay, we're getting weird. All right, so if I can do wet beads, what's the difference between wet beads and this stuff? Stuff they call oobleck, which is cornstarch mixed with water. Have you played with this stuff as a kid? You know what this is? It's literally what I just said. You take cornstarch, you add water. Done. And yet, this material behaves really strangely. So this is what happens. This is what cornstarch looks like under a microscope. It's small particles, right? And when you get them wet, an interesting chemical thing happens. So don't let me explain it. Let's let Ellen explain it. So this is before Ellen got kicked off the air. She used to have this, like, I don't know, this crackpot science guy on the show every now and then who would do experiments with her. They had one whole episode dedicated to oobleck, which is what you call this mixture. Okay? And so what's interesting about it is it's very gooey. You know, it feels like a weird fluid. But if you interact with it very forcefully, you can solidify it. And you just roll it into a ball. You just drop it and it just melts. Okay? Yeah, like I said, it feels like goo if you're calm with it. But you can punch it and it just turns into a solid under your fist. Watch. Pretty weird, right? You know, a little audience participation, I guess. So you can run across it, which is fun. She's very proud of herself. But you can't walk, right? What happens if you walk across it? You just sink, right? Okay. So I've seen many talks on this material. If you study rheology, you certainly know many people who've looked at this. Okay. But I looked at it and I said, we've got this two-phase continuum model that separately handles both the solid and the fluid. We have like a big arsenal here that we could use. What's the real difference between wet beads and cornstarch mixed with water? Okay? What's the real difference, right? Both are particles that are wet. So let's talk about why cornstarch does this. And I'll briefly explain what happens. So, by the way, do any of you study cornstarch mixed with water? No? Okay. Back in Marseille, people do a lot. Anyway. So cornstarch mixed in water. When you get cornstarch particles wet, something interesting happens chemically, which is they develop a repulsion. The particles actually repel each other. Right? So imagine I have a wet granular material where there's mutual repulsion between the particles. So what does that do? Right? So what that means is if I have a wet cornstarch, its packing fraction can be quite high, and yet it can still flow. Why? It's because the grains are always pushing, there's actually this repulsion against each other that leaves a little room for a layer of fluid to get between them, right? So with cornstarch, as long as I'm very slow, I can actually make it flow at an extremely high packing fraction because water keeps getting between the contacts and lubricating them. Now what happens is if I'm too forceful, I'm going to squeeze that fluid layer out, and then I get true solid on solid contact. The friction will suddenly turn on and go, oh my God, I'm totally consolidated. And then it looks like the strength just jumps right up, okay? So really, what I have to do is to think about how to model the interplay between how many contacts are lubricated and how many contacts are now not lubricated and solid, right? And so this is the model I have for wet beads. And you ask yourself, what has to change to model this effect? And in brief, the answer is these two numbers. So remember this number here. So what is phi m? Phi m, right, is the highest packing fraction at which I can have a steady flow. Okay? Now, when I add this repulsion effect, depending on how many contacts I have, it will change this number. All right? So Weird and Cates, back in 2014, introduced something called the fraction of frictional contacts variable, F. All right? With this idea that this critical packing fraction for flow depends on how many of the contacts are frictional versus lubricated. All right, and if you're really frictional, you'll get the sort of the close packing limit that you get for frictional particles. If you're really lubricated, you'll get the limit that you get for completely frictionless particles. And that's the difference, right? And in between, it's some kind of mix of those two values. And this thing here is a rate sensitivity parameter as well. And so what we're going to do is introduce an extra state field that tries to measure how many of the contacts on average in my continuum are frictional versus lubricated. And we're going to use an evolution law that we developed based on some of the physics people had developed for this stuff. And so we wrote this evolution relation. What was nice is, if we just run our model, we get what are called shear thickening curves. All right. So if you look at shear rate versus shear stress, where you control for packing fraction of your cornstarch mixed in water, you get really wacky looking curves, okay, that go from sort of continuous shear thickening to what appears to be discontinuous shear thickening. But all we've done is to add that extra state variable into our wet beads model. That's all we did. So here's what we're going to do. This is our comparison of our model calibrated to the data from Hermes. Let's snap our fingers, let's use that calibration and see what it predicts in more interesting geometry, shall we? How about this one? So Waitukaitis and Jaeger had a bucket full of oobleck, and then they shot a rod at it like this. This is in slow motion. So the rod, that's its reflection down there. So do you see the pock marks forming? That's because it's solid. Okay, you're starting to see solid material growing from the impact site. All right, and we're really interested in that, trying to capture that front as the solid grows out from the oobleck. All right, so what we did was we tried to mimic that on the computer. All right, so this is their data following the velocity of the rod as a function of time. You get a huge jerk in the beginning, but then like when it slows down, it can kind of sink through again. That's what they're seeing here. And this is, I believe, an ultrasound measurement that shows what the displacement looks like under the rod. And here's what we got when we shot a rod at our material, right, using axisymmetric MPM. And indeed, we get a kind of a similar displacement pattern. But what's interesting is after this, Han et al. Did a more controlled intrusion where they took a rod at assigned speed and pushed it through and did really careful measurements of what was the displacement field in the oobleck underneath it. So this is what we found in our simulation. You can see the velocity field. You can see these zones of displacement. You see this thing growing as you come out. Okay, and what's interesting is we got very, very similar relationships that they found in terms of this front over a function of time. So this front grows downward and sideways, okay? And it's interesting because this downward length is about twice this sideways length. That's what they observed in their study. And that's actually what we're seeing as well. The longitudinal versus transverse fronts differ by about a factor of 2, which was pretty interesting to us. So if you actually take a rod and push it into the oobleck and you watch that solidification front grow, the model is able to capture that front. And for fun, of course, we had to do this one. You can run on it, but you cannot walk. Okay, so this field variable is F. Remember I invented a new field variable that says basically how many of the contacts on average are frictional versus not. When F is large, you get lots of frictional contacts. When F is small, it's lubricated contacts. And so you can kind of see in this video here that every time the runner slaps the surface, it solidifies the material. You see it through the F field. You see how F is going up? It's turning it into solid. Whereas this poor guy can't solidify the material around it, so it sinks. And if you look at the velocity, you really see it. So the guy who's running up here, you see that the velocity under it looks like a rigid body rotation. That's because it solidified all that material, and now it's just rotating. But this one down here is just, it can't solidify the material around it, so it just kind of spins in place. How am I doing? I'm pretty late, aren't I? Okay, I'll just show you some fun movies then. We created a new method for the fluid phase to let us do air better. What I showed you is pretty good for liquid, but not for air. So for air, we created something called the finite volume MPM method, where we do the same idea, but the domain for the fluid is not MPM points, it's finite volume method. So we had to create a way to do that. But then what's fun about that is you can do like turbulent motion in the fluid with more accuracy. So this is a gunky pipe. that you tilt. And you can see the fluid starting to flow over it. And the solid is still MPM, but the fluid is now a fixed grid finite volume method. So you can see it sloshing around and doing all that fun. And so that's complete mixture theory, same basic model, but now the fluid is solved with the finite volume method rather than MPM. Or, I don't know, let's say you have a sand dune and you blow really hard across it, right? So this is what will happen. And again, remember, this is a continuum. Those are material points. You get that kind of crescent shape at the end, which is kind of fun because that's what you see if you ever go to the desert. So you always know the wind direction in the desert by where the horns are coming out of the sand dunes. This was something observed by Bagnold in the 1950s. And the guy who did this work was an aerospace student, so we had to do something involving a rocket. So it's hard to find rocket designs online, but you can find old ones, all right? So this was the design for the rocket engine of the Eagle, which landed on the moon. Remember, the Eagle has landed. So that's the Eagle rocket. But he simulated it on Mars. So this is what happens if you take the lunar rocket and you blast it off on Mars. So this is Martian soil calibrated to what we know about Martian soil and Martian air. All right, and so take a look at the Mach numbers we're dealing with here. So Mach number is M. So this is a thermal compressible gas model being solved with the finite volume method. And you see it's kicking up the material everywhere. It's very, very fast stuff. So anyway, I had to speed through that last stuff, but long story short, I've taken you on a little bit of a journey that started with how to model a dry material, how to do it with a meshless method, then how would you model a mixture of two, then how to do those with meshless methods. And the nice thing about it is, my philosophy, I'm no longer limited by complication. Just because a model is hard doesn't mean we can't simulate it now. I can do two separate phases interacting. You just have to tell me whatever the model is for those things and we can run it, which is sort of nice. And it beats the alternative, which is vigorous, loud ego, where you just tell people that your model would do something. No, you can actually show people what the model can do. You can really simulate these things now, which is nice. Yeah, baby, I'll take your questions. There you go.
Thank you very much. Thank you very much. Maybe one or two questions.
Thank you. Just a quick question. It seems that when you have interfaces between phases, like the dense solid phases and the liquid phases, sometimes there is some kind of droplets or bubbles that are that seems unphysical.
Sorry, can you give me an example of which problem?
For example, for example, this one.
Oh, the dune, this one?
Yeah.
Okay. So tell me know when you see it.
Now, like those kind of small beads.
What are you talking about these? Or are you talking about these?
The one on the solid.
Yeah.
Yeah. Like you had also the same on the collapse of the granular.
Oh, you're talking about the points coming apart.
Yeah.
Yeah. Those aren't bubbles. Those are material points coming off the other points.
Okay.
Yeah.
But it doesn't seem that they merged back.
I think they do. Let's take a look. If you just wait, they'll come back in, right?
Well, we can see some pocket of.
Yeah, you might see a relic of it. Yeah, that's true. But I think it's also in a different stress state, right? So it came from something else. So, but they're in the same element now. So it might look like that, but their homogenized response is now making the elemental stress.
Okay.
Yeah.
And on for example, on the collapse of the granular column,
Mhm.
the water, we can see on the low volume fraction, there is some kind of bubble at some point that are on the free surface and wiggling around. Do you think it's a problem?
Let's see. Is this with this one?
No, on the
Up here.
on the like air fluid interface.
Oh, the air fluid interface.
Yeah, right. Here
Up
we
here?
can see them not on the video of the bottom.
Oh,
you can
okay.
see some kind of gray dots wiggling around.
Yeah. Oh, yeah. Sorry, you're talking about. Just want to make sure I know what you're talking about. Are there? You just.
now.
Oh, like little bits coming
Yeah.
out. Yeah, yeah.
Like, do you think it's a problem or?
Let me put it this way. When it comes to simulating a fluid with NPM, it's not the best method. There are little issues that can happen in the fluid with a meshless method. Part of the reason why we invented the FV approach, the finite volume approach, which is a little bit better at this. Yeah, you can. So the nice thing is you get Lagrangian features. It'll slosh around. I haven't really noticed this before. I don't know what the answer is to this. If there's stuff jumping out or not, I can't really tell. But it seems to come back, right, and then joins the rest of it. Yeah, I don't know exactly what that means. I hadn't noticed that before. Yeah.
I saw the experiment. The simulation seems to be very close to the experiment.
Oh, okay. Yeah, they're the Rondon paper. Yeah.
Please.
Thank you for the talk. I had a question about the rate dependence of friction in the dry granular media.
Mhm.
You think it doesn't play any role? Did you try?
Yeah.
both
So
and
yeah. Here's my take on that. Rate dependence in a granular material is important if you're interested in free surface flow. So let's suppose you have a chute and you want to know what's happening right at the free surface, right? There you'll definitely want to include rate dependence. Now, once you're in, let's suppose you're buried in granular media, like something's moving underground, there, what we call the inertial number I is almost always just about 0. So you can model it with rate effects, but in some sense you're wasting your time because I is basically 0 and mu is pretty much independent of I in that limit. And it's very interesting how quickly that happens. I'll show you something fun. So we did a very special test of the bullet simulation. Okay, so we did a thing where we shot the bullets into the granular media and we compared it to the experiments. And this was mu of I. Okay, so in these tests we turned on the rate sensitivity, which you're always welcome to do, right? And we looked at how deep the bullets shoot into the granular media, right? Now, you might think to yourself, shooting a bullet into granular media is pretty fast, right? So we said, okay, how about we turn off the rate effect and we just make it constant friction? How much different would it be? And the answer was that the depth changed by only like 2%. And that's because, yes, it's going fast, but the stuff that's going fast is under extreme amounts of pressure, right? And I is a mixture of flow rate and pressure, so it's still pretty small. So when you actually look at stuff like this and you ask, where is I significant? You're going to find it's this material up here, right? The stuff near the free surface where pressure is low. So once something is sort of getting down into the material, I very quickly becomes irrelevant. Yeah, it's really a free surface phenomenon. It's important if your solving methods require rate sensitivity to include I effects, right? But if they don't, if you can do plasticity, so for example, plasticity theory doesn't require that, and that's what we do. So we can just turn it off entirely and just go dry if we would, dry rate independent if we prefer, or we can turn it on. Yeah.
okay, thanks a lot.
No problem.
So okay, thank you very much again.
Okay.